Okay, I wanted to do a graphing tutorial here and go a bit more in depth. Suppose we've found some eigenvalues and some eigenvectors, and here's a direction, an eigendirection as I like to call them, associated with an eigenvalue of -3, and this one down here is associated with an eigenvalue of +2. And suppose we take an initial condition like 4, 0. The idea is to understand conceptually why we can sketch a graph. Conceptually, we expect, since this is the solution down here, that this point, which is itself a vector, composed of these two eigenvectors. In fact, we can sketch a, sketch a parallelogram, something like this, and maybe like this. So when we start out initially, the system, x1, x2, has some amount of stuff in this eigendirection and some amount of stuff in the other eigendirection. And the coefficients turn out to be 4/3 and 4/3, which look about right. Now it's not 4/3 of a unit, but 4/3 times that vector. So I've marked off equal increments along this eigendirection. They're all √5, which is the length of the eigenvector I'm using. And then I've marked off equal increments along this one. They're all √2, which is the length of this vector. So we have 4/3 in one direction, 4/3 in the other. And as time starts, we're going to see a faster decrease of this component than this one grows. So in some amount of time, this will decrease by an amount, and this will increase not quite as much. And that'll create a curve, where the curve indicates that this point is being, I like to say, kind of, drawn or or funneled towards this line as it's going out. And I want to show you that with some calculations. So let's look at it. What I did was go ahead and crunch a bunch of numbers of these two exponentials. So we have e to the 2t, e to the -3t. And at 0, they're both 1. So we're at our 4/3, 4/3. And then we're going to go by tenths of a second, or tenths of a unit of time here, because e to the 2t, when t is 1, is 7 something. And e to the -3, so when t is 1, is just a hundredths of a unit. And those are not going to be doable on this graph. So let's run through what's going on here. So where does it go next after 1 unit of time? So I can take the first component, or not the first, this first component, and take 4/3, and I can multiply that in the view here. Multiplying by, well, what is e to the 2t when t is 1/10? 1.22. So that means it's going to be 1.6 units in this direction. So 1.6 is about 1 2/3. I'll be right about this much. And then conversely, my other value, at the tenth of a second, the e to the -3t is only 0.74. So we're actually calculating points here. So it's a little less than 1 unit. So right around here. So let's illustrate this. Let's do it with pencil. So we're going from here. This is the first increment of time. It's a tenth of a second. And here's our first increment of time. Oh wait, yeah, I jumped. What did I do? Yeah, I jumped too far. Whoops. 1.6, not 2.6. So that would be more like right about here. So here we go, delta t. So we go to 1.6 units in this direction, and I'm goofing several times. No, I'm fine. Yeah. All right. So what does that give us? All right. So now let's try to make this look about right. You do a parallelogram, and now we're right there. That would give us a point right here. So that's where this system is going to move after 1/10 of a second. So let's do another calculation. I'll do a couple more slowly, and then I'll speed it up a little bit. So we still have 4/3. That's the coefficient here. Let's go to 0.2 seconds. So for the e to the 2t, that's going to be the 1.49. So times 1.49. That gives us almost 2. So we'll be up here. Right? And then 4/3 times at 0.2, e to the minus 3t is about 0.5. It's 0.55. That's about 3/4. So, you know, maybe about there. Not quite. So we can again do like a parallelogram law, find out where the vector is then. Now you wouldn't do this in practice, and also I'm not the scale. But doing this once might give you some understanding numerically why this is happening. All right, let's do one more. So this is another delta t increment, another delta t increment. Do one more, and then I'll pause the video and fill in the rest. So this is 4 divided by 3 times. So now we're at 0.3 seconds. So that would be time 1.822, which is 2.4, a little less than 2.5. So we'll be at about right about here is the next jump. And then 4 divided by 3 times at 0.3, e to the minus 3t is 0.41. So this gives us about a half. So I just wrote about halfway, maybe about there. So I'm just sketching these parallel lines because we can find the resultant vector in this fashion. All right, so there are some points. I'm going to pause the video and do the rest. All right, so I've gone ahead and put those points in, and I went back and corrected this one a bit. If you want to be extra careful of this, what you can do is you can measure how long a unit is in this direction. This is 28 millimeters. And then whatever answer you get, if it's less than 1, even more than 1, you can multiply by 28 to find out how many multiples you should get in terms of millimeters. And then you can measure off the distances. So as things got small here, I tried doing that a bit more often. I can only go up, not even to a full second, because before a full second is up, we're already way down here. So these are all 1/10 of a second apart, and there's several things happening. One, you have that fast initial decay from the -3 exponent, and while that's happening, you also have the exponential growth with the exponent of +2. And you can see here, this is typical, all right? As we get smaller and smaller and smaller, or as time wears on, the decay decays more slowly, right? Exponential decay flattens out. And as time wears on, exponential growth increases. So these little arrows span larger and larger chunks of space. So again, this is not the way you would do this for any assignment. And a lot of times, it seems really tedious to students. But working through an example like this really carefully, seeing all the numbers, using the parallelogram law, you can perhaps get a bit more insight into why the solution looks like this, getting a sense for how the different exponential functions or not dueling per se, but you have this particular decrease going on. At the same time, you have this growth. And as you're chomping the numbers, you can see that these points are getting further and further apart. That's also worth saying. So again, notice in these graphs that time isn't visible. These points are all equidistant time apart. They're all 0.1 seconds. Because 0.1 seconds is going to get further and further apart due to exponential growth in this direction and exponential decay in this direction. Now, it's worth considering, what would happen if these numbers had been switched. What if this was something like a 3 and this was something like a -2? Then we would see what would happen. Well, you'd have slower decay at first and faster growth, right? So I don't know if it would happen exactly for these two. It might still be quite curved. It would definitely still be quite curved, because we know we're still going to go in this direction while we're decreasing. So there's still going to be this sort of rightward concavity, but it'll be less shallow. And the greater the difference between these two numbers, the greater, this curvature is going to be. So I hope this is helpful. You should try to verify these numbers, see if you can do it yourself, get a sense for what this is actually saying about the system. These systems of equations are describing several things happening at once. This could be position and velocity, it could be two types of shrubs, it could be a concentration of a drug in two organs, or the mass of salt in a couple of interconnected barrels, any number of things.